Okay, so welcome to the rest of week 7 proper. Hope the motivation was useful. I'm going to start with a tiny little bit more before we go into the definitions. We're going to be looking at curves. That's with a view to us mastering a very important technique, which is integrating one-forms over curves. So just to give you a sort of sense of the direction that we're heading in, let me take two-dimensional space, A2 as we are referring to it, and let me imagine that there is an electrical charge at the origin. An electrical charge. Let's suppose that's positively charged. And let's suppose that there is a particle P that is travelling in a path along in a way, something like that. And let's imagine that this particle P is also positively charged. So it's going to repel the electric charge here, and the amount that it's repelled by is going to depend on the distance between the two things. So that tells you something about the amount of force that it's experiencing at each point. One thing that you want to know when you're doing a calculation like this, or considering a situation like this, is how much work do you have to do when you're pushing this particle around, right? So how much work do you have to do against the force that you are experiencing from the two particles repelling each other. So how is work measured? Work is measured as an amount of displacement, so a distance times a force, so the magnitude of the force. So if we remember that work done equals, I'll use a delta to represent displacement, multiplied by force, then let's work out something about this situation relative to what we've been doing so far. So work done is an amount of energy, it's a scalar quantity. This displacement is going to be a vector, so I could be looking at a point here, right? So I might imagine a tiny amount of displacement along this curve. Let's turn that into a tangent vector of a certain magnitude. And then what this force therefore is going to do, if I'm going to use it to calculate the work done, is it's going to take this tiny amount of displacement that I've got here, this vector in a tangent space, and produce a scalar. So what are the things that do that take in a single vector and produce a scalar? They are precisely the one-forms, right? And when you add up, when you integrate all the tiny amounts of displacement times the tiny amounts of force, you are precisely integrating a one-form along a curve. Okay, so we will eventually, and this is going to happen in week 8, integrate one-forms along curves. But we want to set up all the definitions and any concepts that we need in advance of that. So that's going to be the basis of week 7. So we're going to start 2.4, and this is going to be curves in a n, so affine n space. We're going to assume we've picked an origin here, so everything is going to be relative to some origin. In order to define a curve, I'm going to need to recall some things about intervals. So hopefully you've seen some notation like this before. A comma b in brackets is going to be where we're thinking of a and b as being real numbers. That's going to represent a subset of the real numbers, and it's going to be the subset of real numbers t in R that are between A and B, but strictly. So we don't include t being equal to A or t being equal to B. We also want some closed intervals, so that's where we use a square bracket, and those are the real numbers, exactly the same, except they also take the endpoint. And then we have we can have half and half, so we can close it off at one end and not at the other. So we'll have all such intervals at our disposal. Let's have a definition. Curve. So let I be a subset of R, be an interval. Okay, given that, a curve C in AN is the image of a continuous map gamma, which takes I into AN. So continuous here is going to mean that we do not want to be thinking of taking our pen off the paper. It needs to be connected at all points. So we'll look at some examples in a second, but we say, let me underline that, let me say that gamma is a parameterization of C. And here, just to unpack the definition, what we're saying is that C is the set of points P in AN such that there exists a T in our interval with P being equal to gamma of T. So this is what it means to be the image of this continuous map gamma. You're saying that we just look at all the P's that we hit from using the map gamma. At this stage, I will make the point that T is not chosen here for no reason. It is very often useful to think about T as being time. So you would think about a particle tracing out some kind of trajectory, some journey that goes through time. So the time could be between 0 and 1 seconds, or 1 hour, or whatever it is. And what this gamma is telling you is if you give me a point in that interval, so that might be 5 seconds in the context of a minute, then I will tell you exactly where you are at that point. Okay. But the curve doesn't care about the parameterization. It doesn't care how fast you go to start with and how far or how slow you end up at the end. And so in fact there will be many ways of tracing out the same curve with different types of gamma. And on that basis we are going to want to look at, we'll come to this next, but reparameterization, so taking two different parameterizations of the same curve, where things can be, maybe the calculations are easier, but we'll want to know then that if we change the way that we parameterize the curve, that the quantities that we're measuring, which could be something like the amount of force that we're applying, so the amount of work that we're doing opposing a force, that those quantities won't themselves change. So that will be the next subsection. But anyway, for the purposes of calculations, it's often useful to put things in coordinates, almost always. So in Cartesian coordinates, so this is where we've got an orthonormal basis of our space that we've picked. We may write something like, let's move on to a new sheet. So just projecting to all of the different orthonormal basis vectors, you're going to get a vector where we can describe it in the following way. So we need n coordinates. These are the coefficients of those coordinates, and because projection is a continuous function, composing two continuous functions is also continuous, it follows that these gamma i's are continuous functions, and they are taking the interval that we start with and they are producing something within a real number because they're just single coordinates. Okay, let's have an example. So this is example 2.32. Obviously the previous definition was 2.31 in your notes. Let's consider the parameterization map. Gamma, which takes a particular interval, in this case it's going to be 0 to 2 pi, but not including 2 pi at the end. And it is going to, so it takes that interval into A2 in this case, where a point at time t is, so the time t is sent to the point a cos t, a sin t. Right. What curve do we get from such a parameterization map? Well, whenever you see cos and sine, you've always got to think about circles. And you'll notice, of course, that if you square the first coordinate and square the second coordinate and add the two things together, you get a constant number, because cos squared plus sine squared is 1, and so you get the constant number a squared. In this case, C is equal to the curve that we get here is the set x squared plus y squared is a squared, which is obviously a subset of A2. And you'll recognise this as the equation of a circle. centered on the origin with radius A, and this is indeed what we get. So a circle centered at the origin, radius A. Now, what I haven't said, what I've actually proved is that we get some subset of this, because I've said that the coordinates here always satisfy this equation, which is called an implicit equation of the curve. But let's just see that we do get the whole circle. If I let t be equal to 0, I do get the point A, because cos of t when t is 0 is 1, so I get A 0. So t is 0, I get A 0. When I move around to pi by 2, I've got to the point that A is equal, so cos of t is then equal to 0 and sine of t is equal to 1, so I go around here, I get t is pi by 2, and that gives me 0a, and similarly if you go around here, that's where t is pi, and all the way back around here, this is where t would be equal to 2 pi. Now I could, we can go around this as many times as we like, we're still going to get the same curve, but the point is we've got it at least once, and in fact, because of the choice of not including the endpoint here, we get it exactly once. So that's the parameterization, that's an example of a parameterization map. In the next video we'll look at reparameterizing curves, and then we'll be in a position to ask whether that affects the calculations that we're doing. The last remark in this section I've already made, remark 2.33, is just saying that time is kind of a very good way of thinking of the interval that you start with, so that you're taking an interval of time and asking where a point is moving in that interval. Okay, see you in the next subsection.